All right, in our last lecture, we started talking about the theory of the maximum likelihood estimator, which is probably one of the most widely used estimator in applications. So before we continue or we do a recap of our last lecture, I want to first ask if any of you have any questions regarding MLE and any confusions you previously had about MLE. Or you think it's quite straightforward for you to do the calculation?
MLE part was, for me, to be honest, like better than previous,
Oh, really?
yeah,
Because you're more familiar with it.
yeah,
I see.
only because of everything, yeah.
I see. But before, how much would you say you know about MLE as an estimator? Its theoretical properties, or like why it is a good estimator.
You mean like when your question is like why that is a good estimate?
Yeah, that's right.
Like you said, like we can almost like an automate the process.
Mm-hmm.
We know the property that certain with certain regularity conditions,
Mm-hmm.
unbiased and
Yeah.
efficient.
And why do you think it's intuitively reasonable as an estimator?
Kind of like makes sense because like you said, the function is like I'm taking the input of the parameter and
output the likelihood value.
so for each parameter, you're testing how much like our data is like likely to be like this.
Yeah, that's right. How likely you're going to observe this data.
Yeah,
that's right. So essentially, you're using your data to guide your choice of the parameter value, right? Your estimate of the parameter value. But why do we need some regularity conditions? That's something we will discuss today in more detail about the distribution. So remember the example we presented last time. I think this is a very interesting, even though contrived, but interesting counterexample. Look at this example we did last time. So this is a case where the MLE doesn't work because the MLE, we said, it will always be close to 1, regardless of where the theta is. And the reason is because for this distribution, we will have a very sharp increase in density value that depends on our parameter theta. As the theta gets closer to 1, the highest density is going to up to infinity. So in this case, the likelihood can be easily maximized, but at an uninformative parameter value. So regularization is actually related to how smooth your distribution is, whether you will have some extremely large density or probability mass functions at some values, or density. I think continuous cases is like most probably like the common case where you have the problem. And this is also related to when we talk about bootstrap. Remember when it failed, it is about when you try to estimate the boundary parameter, right? So whenever you see we have this counterexample, I think a lot of our counterexamples, and we'll see that again today, are constructed for the case like uniform distribution between 0 and theta. Theta as the upper bound is something we want to estimate, right? So for such cases, it's very irregular. Why is that intuitively? It's because your density doesn't have a smooth change. The density function is not continuous. You basically have a sharp drop of your density value from whatever constant, like 1 over theta, in that interval between 0 and theta is uniform, right? So density is 1 over theta. And then you drop down to 0 all of a sudden at the value of theta. So this is a case where you should be very cautious about. But on the other hand, our intuition told us, especially from all the previous lectures, that if our parameter is something related to our population moments, which is expectation of something, that is usually something easy to or nice to estimate. Even for the V statistic, U statistic, they are for the so-called expectation functionals, right? So the parameter, no matter how complicated, is still depending on some expectation. And whenever it is an expectation, you can use the average on your sample as an estimator. And central limit theorem give you nice properties about the normality, asymptotic normality for such estimator. So I think that is the most important take-home intuition from this class. Like what kind of estimators are good and what are easy to estimate problems, or like distribution-wise, why for some distributions it's easier to do the estimation than others. But honestly, I feel like nowadays, these kind of discussion, especially related to, all the things we talked to so far, are related to maybe except the density estimation part. That is called non-parametric estimation, because we're trying to estimate the density function, right? Not a parameter of finite dimensions. But for most of the cases, when we talk about parameter of finite dimensions, their estimation efficiency, a lot of the counter examples were actually based on parametric distributions that are not so natural, especially like this case, right? This is not a naturally observed distribution. So they are more like mathematical, how to say, constructions, mathematical construction. So how useful is that for your research? I think maybe the usefulness is more like why we learn mathematics. For a lot of the things we learn is about operations, it's about computation. That is obviously useful. But for many other things like abstract thinking, logics, they're not immediately useful, but at least it can make your thinking more rigorous. That's what I think, right? So you can think out of the normal things you observe and think about the extreme cases. Maybe most of the cases they won't happen, but in some cases it can make your argument more rigorous. And that is still the thing I think is, I value that. And so I think that is also something that statistical training can be useful for data analysis. Okay, so coming back to the, how to say, nice properties about MLE, we talked about these conditions last time. Sorry, let me move myself away. So first one, regarding the distribution, regarding the identifiability of parameter, this is a must. Okay, C1, identifiability. Second thing is the parameter space being open. Okay, open set. The third one is regarding IID sample. Okay, it's the IID sample we use to estimate MLE. Then that's about sample. And the fourth one, very, very important, that is the non-zero density domain of your distribution must be independent of your parameter of interest. So that this excludes that uniform 0 to theta case, because therefore, in that case, the non-zero part depends on theta. Finally, C5, differentiable with respect to theta. And so we can actually write the first derivative against theta as this or this. So it's about differentiability. So we talked about those before last time. So continuing from there, we want to say first give you the conclusion before we prove it. We'll give you more detailed discussion later in today's lecture. So this is the most important asymptotic normality result for MLE. So these 5 conditions, sorry, I forgot to say that, is to guarantee this C1 to C5 are to guarantee the consistency of the MLE. In other words, the MLE will go to converge to your true parameter theta in probability. But consistency is good to know, it's a good property, but it's not useful, right? It's not useful for us to get a confidence interval for our true parameter. But asymptotic normality can be useful. And this can be considered as a generalization, again, of the central limit theorem, except that here, we're not looking at a sample mean and the population mean, as in the central limit theorem, but we're looking at MLE and true parameter. And this is more general, right? Because a lot of our estimators are not just sample mean or any source of means. Okay, so the most important result in this is the asymptotic variance. It's 1 over Fisher information at theta. And we're talking about this single parameter case, one-dimensional case. What is Fisher information? So let's first introduce the definition, and then we will introduce some alternative definition under more conditions. So the straightforward naive definition, or I would say the first definition, is defined based on the expectation of the square of the first order derivative of the log likelihood at theta. Okay, so we are actually taking the derivative of log likelihood instead of likelihood. And because of this chain rule, this inside expectation this can become just 1 over f theta at x times f theta prime at x. So this is the derivative of the density itself, okay? And here we're just expressing this expectation in terms of integral. So that's what we have. And this Fisher information, what does it measure intuitively? First of all, we think of expectation as an average, right? Average over the distribution of x, random variable x. Since x can take different values with different weights, we take the weighted average. That's expectation. And what else do we have here? It's a square of something. And this first order derivative is basically measuring the change at theta, at a particular value of theta of the log likelihood. Okay, so then let's look at x. Think of x as our random observation, one observation. Given this observation, we can calculate the log likelihood. And then we evaluate how fast does this log likelihood change at a particular value theta. And this is a change at one observation. Now we take expectation for this observation across all its possible values, and given the weight, right? Given the probabilities, that's what we have. And also by taking the square, essentially we don't care about the change, the sign of the change, whether it's increasing or decreasing. We don't care about that because the derivative carries sign with it. By taking the square, the sign is gone. It's only the magnitude of the change. So what does it mean here? It means that if the change has a large magnitude, large derivative in absolute value, then it means that given the current observation, we can easily see how much likelihood, or given the current value, the likelihood will change a lot at my current value. If it change a lot, then we can more easily detect this value, right? Because if it doesn't change a lot, then at different theta values, maybe I will have similar log likelihood. Then it's more difficult to distinguish those theta values. But if it changes a lot, then it's easier to distinguish the theta value. And I'm looking at this thing in an average sense across possible x. So that's Fisher information. Yeah, so that's why we say the larger the Fisher information, the more we can learn, we can estimate theta by MLE from our data. Okay, yeah, so that's the intuition here. And also the larger the Fisher information, the smaller the asymptotic variance. That's also nice. It can be smaller asymptotic variance means that the estimator is sufficient. Okay, but of course, since you are going to have this 1 over Fisher information I theta, this is an inverse, and then by default, you don't want this to be 0 or infinity. Because if it's 0, you have the dividing 0 issue. If it's infinity, you have a 0 asymptotic efficiency, asymptotic variance. That means this multiplying by root n is not enough, right? It still go down to 0 so quickly. So it has a 0 asymptotic variance, means that you're convergent to a point mass at 0. Then you would wonder to how to make this bigger, right? Maybe from root n to n, then we can have a stabilized asymptotic distribution. Okay. An exact statement as proof of this basic result will be given in our next section. So first, let's do some illustration. Poisson. If x has the Poisson distribution p lambda with this probability mass function, then we're just doing the Fisher information calculation. Okay, we take the log of this and then take derivative against lambda. This is what we get. And then if you take expectation of that, you're just taking this 1 over lambda out of expectation as square, expectation of x minus lambda square. And this is just the variance formula, and that's lambda. So we cancel out 1 lambda, it's 1 over lambda. So essentially, now you apply the asymptotic normality result for MLE, because we know here the sample mean is the MLE. We already see that. Then essentially, this is MLE, this is true parameter, this is 1 over Fisher information, and that gives us lambda. So you see, this is based on the MLE result, but we will get the same result as central limit theorem. Because here, X bar is sample mean, lambda population mean. And lambda is the, how to say, one data point, one random variables variance, right? Poisson has variance lambda. So that's why this is central limit theorem. Okay, how about normal? For normal distribution, this is something we talk about. So we look at both the mean and variance. We call the mean cosine, we call variance sigma squared. We can consider easy cases where when fixing sigma, we can have the facial information of the mean as this. When we fix the mean, we can actually have the facial information of the sigma, which doesn't depend on the mean. That's very important. It means that if you're just by trying to estimate the variance, the information has nothing to do with the mean. And this is something very important for normal, because normal you can shift your mean, right? And it has the same variance. So that means estimating the variance has nothing to do with the mean. Yeah. But estimating the mean has something to do with the variance, because the larger the variance, the more spread your data are, then basically estimating this mean is what? It's more difficult. Yeah, because your data is more spread out. If sigma is small, your sample will be concentrated on mean, then it's better estimator. Okay. So these are the intuitions we can see from this. So in both cases, you can actually show that the result using the asymptotic normality of MLE will be the same as using the central limit theorem. But there's a more interesting case in which we specify the mean to be A times sigma with A being known. So in this case, we reduce the two parameters to one parameter because the mean is just a fixed multiplier times standard deviation. Then, if we still want to estimate sigma using a single observation, we write down the log likelihood in terms of sigma, because now mean is expressed as A times sigma. And then its derivative with respect to sigma, we take the derivative. And then we're going to square this whole thing, and then take the expectation. That's our Fisher information. So we go with that definition. So I skip all the algebra details. I will show you that the Fisher information turned out to be this. Okay, and with this Fisher information, now you just apply that MLE normality, asymptotic normality result. This is what you get for this case. Okay, so essentially it showed you that these are just practical example practices for showing how to use the asymptotic normality of MLE. So nothing beyond that. Because for this one, it's not so easy to directly use the central limit theorem. Since now the mean and variance are tied together, but you just know the ratio A. Okay. And it is often of interest to estimate not theta itself, but some function of theta. So now we talk about this reparameterization or parameter transformation perspective application. So in this case, our parameter of interest is not theta itself, but eta. Okay, and we know eta is a function of theta. In some applications, maybe the parameter you are interested in is not just a natural parameter of your distribution, but some transformation of it. So if you know that this g is increasing, strictly increasing, then this g function has an inverse. Then you can express theta in terms of eta. Then you can actually rewrite your density function in terms of theta to be in terms of eta. And then you would take differentiation against eta for the log likelihood of eta, and you follow from there. But just for now, I'll just give you the conclusion without reading the detailed text here. So here, this is a result saying that if G is continuous, this is the key thing. G is a continuous function of theta. Then by applying G to your theta MLE will give you an estimator of eta, and this is consistent for eta. So in other words, I'm just translating this to be like if theta n hat converges in probability to theta, then eta n hat converges in probability to eta. Yeah, nothing else. It's more like the continuous mapping theorem, right? We're applying that. And 7.1.1 corollary, let's take a look at the condition here. The condition here is just This one. Under the assumptions of theorem 7.1.1, if the likelihood equation has a unique root, which is our MLE, and then MLE is consistent. Okay, so this is something we are using. MLE consistent, then continuous transformation is consistent. All right. Okay, now let's talk more about feature information, which is very interesting to know. And here we want to clarify that there are some misconceptions we may have about it, and we will try to avoid those misconceptions and then try to use or interpret feature information properly. So the quantity I theta defined as this, let me just write it again. Expectation of this d theta log f theta x square. This is definition of feature information, right? The expectation of the square of the derivative of log likelihood. Okay. It is coefficient information or the amount of information about theta containing x, a single observation from f theta x. However, the suggestive term information should not be taken too seriously. It is justified mainly by the fact that, in many cases, under assumptions and with restrictions that will be made precise in section 7.5, 1 over I theta is the smallest asymptotic variance obtainable by an estimator delta m satisfying a limit relation of the form. So essentially, this is about asymptotic variance, okay? And we take the denominator as of information because the larger the information, the smaller the asymptotic variance. Although we speak of the information contained in a single observation, x, the justification is just primarily based on the assumption of a large sample. To see what I theta has to say about the informativeness of a single observation, note that this logarithm derivative, something we saw just now, is the relative key thing, relative rate at which the density changes. So you are looking at the change of the density in relation to the density value at the current x value at the point x. The quantity I theta is just the expected square of this rate. It is plausible that the greater this expectation is at a given value theta 0, the easier it is to distinguish from theta 0 from nearby values of theta, and the more accurately therefore theta can be estimated at this theta 0. In this sense, the larger feature information is, the more informative is x. However, this is the key thing. This argument leaves many aspects of the relationship between x and theta out of consideration and provides no basis for thinking of I theta as a comprehensive measure of the amount of information contained in single observation. We will show you one counterexample, so in which the observation is still informative, but unfortunately, feature information is not big. It's actually 0. Okay, let's look at this example. An informative observation with 0 feature information. Let x be normally distributed. So in this case, we're not estimating the mean, but we're estimating the cubic root of a mean. So we specify theta to be the cubic root of mean, and then the mean is theta cubic, and the variance is known. So in this case, when we write the likelihood of theta, it's this one. So in terms of the density, now we need to put theta cubic here. Okay. And then if you take the this is the derivative, and this is the Fisher information. So I skip the details. I just want to give you the result. So this is the Fisher information in terms of this theta. And you can see that if you set the mean or theta as a mean cubic root to 0, then you will have Fisher information equal to 0. That's not good. Because previously, for the normal case, remember what's the Fisher information. If you're interested in estimating the mean only, this is the Fisher information. It's 1 over sigma squared, only about sigma squared, not about the mean itself. So that's why when mean is 0, Fisher information remains this constant, 1 over sigma squared. But with this cubic root as our parameter of interest, theta, its Fisher information actually depends on its own value. So when it's 0, then Fisher information is 0. However, it doesn't mean that our sample is not useful, because we can still use our sample to estimate the mean, and then taking that estimate with the cubic root, we can actually get its estimate for theta. So in this case, the Fisher information in this sense is not so useful. Yeah. For this, yeah. So this is the case where that asymptotic normality of MLE breaks down. So we cannot use that result, essentially. Yeah. Yeah. So therefore, even the asymptotic, okay, so basically we need to make sure we can apply that asymptotic normality result. The condition for that holds, which we'll see very soon. Then the asymptotic variance as 1 over Fisher information makes sense. And that's when Fisher information makes sense. Okay. Even the asymptotic justification of I theta works only in the regular kind of situation in which 7.1.27 hold. What is that? This is the problem with the textbook, right? This is it. Yeah, this is what it is. The asymptotic result holds. Yeah, I think they could just write it down. Yeah, instead of asking to go back. Yeah, maybe this book was published in the time when people still read like paperbacks. So yeah, but now with electronic PDF, it's even more inconvenient. To see the difficulties that arise without a restriction, consider the following non-regular example, which violates C4. What is C4? C4 is that the non-zero density domain does not depend on theta. It's that thing. Okay, we violate this. Okay, again, uniform is a counterexample. Let x1 to xn be IID according to the uniform distribution U0 theta, so that the likelihood is if all your x1 to xn are between 0 and theta, this is their density product, right? Uniform 1 over theta time multiply n times. 0 otherwise. If one of your observations fall out of this window, then density is 0. So it can be shown that the MLE is equal to the maximum. You want to maximize this. Maximum, the largest of the x's, that is. And we know this result. Remember, we talked about this when we talk about extreme order statistic. N times the maximum minus the boundary follows what? Something like exponential distribution, right? Minus exponential distribution, because this is negative. So, if this converges to a non-degenerate limit distribution, non-degenerate means that it's not a point mass, it's a distribution that can take multiple values. So if that's the case, then if you decrease this m to root m, so you're not multiplying m but root m, then in this case, this will go down to 0 much faster. Since you're multiplying a smaller thing, right? And this will go down to 0 in probability. So essentially, if you trust that asymptotic normality, then what does the 0-point mass tell you here? Because from that result, you thought this would be, this is your thought, right? Based on that result, if you just apply it. But if you also trust this result, then this will tell you that asymptotic variance is essentially 0. And being 0 means Fisher information is infinity. So you can just conclude that this will tell you Fisher information is infinity. However, if you do the Fisher information calculation yourself, this is the density 1 over theta. We take the log of it, and we need x to be less than theta. Then we take the derivative of this log density. This is it. And then we take the integration. This is it. So Fisher information is not infinity, but it's actually 1 over theta. So this tell you what? Going back to here, it means that this must be wrong. It cannot hold. Because if this asymptotic normality holds, we will see Fisher information as infinity. But it is not. That means that in this case, the asymptotic normality breaks down. Okay, so because we don't satisfy that condition C4, the domain irrelevance to theta, that's why here we cannot just apply that result. Okay, so at least I think this tells you that you cannot blindly apply that result, right? You need to make sure the conditions hold. Yeah, so this result told us Fisher information I theta so inadequately reflects the information supplied by even a large sample about theta. As pointed out, the logarithm derivative, this one, is just this one. We're talking about this, just minus 1 over theta. On which I theta is based measures the change of density from this theta 0 value to this theta value. We measure the change of that log density. So this is the log density at theta 0, log density at theta. However, it disregards the additional and in fact much more important change at the endpoints theta 0 and theta. That is the upper bound in this case, where the density changes abruptly from positive value to 0. So that's why when the domain is involved in the parameter, it is tricky because you will have a sharp change in density, not just change in the log density derivative. Yeah. In line with these comments, we shall restrict the use of the measure I theta Fisher information to regular situations. Yeah, this is where we would define regular. What do we mean by regular situations in which this one holds? This one, again, is the asymptotic normality holds. And we shall interpret the statement that the Fisher information is the amount of information about theta simply in the sense of asymptotic normality. Yeah, so essentially you first need to check the assumptions about asymptotic normality. Then you can use Fisher information to interpret. Because if asymptotic normality does not hold, Fisher information is not informative. Okay, let me just try to reiterate this. First, check conditions for asymptotic normality. Okay, check this first. Second, then interpret Fisher information. You only do that. Otherwise, that Fisher information may be uninformative. Okay. And next, we will talk about alternative expression for Fisher information, which is also commonly used in many cases. Again, C1 to C5 should hold, and we have stated this for many, many times, right? So the same C1 to C4 we recapped in the beginning of the class. So if you need another recap, let me just try to scroll back again because we just kept using this. This is it. C1, identifiability, C2, open parameter space, C3, IID, C4, domain not depending on theta, C5, density differentiable. Okay, so we have these things. So suppose that they hold and that in addition, we have C6, okay? What is C6? This is some additional condition you need on your density to get an alternative definition of Fisher information. The derivative with respect to theta of the left Sandel equation, this one, this is just about the density integrates to 1, right? We're trying to say that you now take differentiation of this by putting it inside expectation. So in other words, this condition is about the exchangeability of differentiation and integration. That's it. So we're just trying to say this. So okay, equals this is the condition. If this thing holds, then we can express Fisher information as the variance of the first derivative of the likelihood, log likelihood. Okay, and previously, you see, the definition was this. Expectation under theta this is the original definition. And we're now saying that if this condition holds, then this is equal to this. So we can have the variance representation of the Fisher information. And what does this imply? Integration and differentiation have exchangeability. This is actually we call the one of the what we call the regular situation. Essentially, it has something to do with that this f must be smooth enough, right? Differentiable. And also there's no extreme value, like the integration does not explode. So you need all of those things to be able to swap the two. Yeah, but essentially for all the functions you think as well-behaving, for example, the function doesn't have infinite values and it's continuously differentiable, this should hold. Okay, and also in this case, since we already know the integration first and then differentiation, we know the integration is integrates to 1. Then that's why we know when we take differentiation, we get 0. But now on the right-hand side, we're saying by putting differentiation inside integration, we first differentiate, then integrate. And this will be 0 because this is 0. Yeah, and that's why we get here. Okay, so the first one is regarding the exchangeability. The second version of C6 is a little bit more. Now we need to have the second derivative exist. So we need the first two derivatives with respect to theta of f theta x exist for all x in A and all theta. So A is the domain of the distribution. And the corresponding derivatives with respect to theta of the left-hand side, again, this thing can be obtained by differentiation under the integral sign. So now for the C6 prime condition, we need one more layer of exchangeability, not just the first derivative, but the second derivative. So we need what we just wrote above, exchange, differentiation, and integration. This is about first derivative. And we need the same condition exchangeability hold for the second derivative. Right, we need this. We need both of them to hold. So added this one more condition, then we can have another definition of Fisher information. It is the negative expectation of the second derivative of log likelihood. And sometimes we use this most often for calculating Fisher information. Because for this one, you just take another differentiation. You don't need to take a square, right? Yeah. Okay. But this has more requirement on the f. It's not just about the regularity of f itself, but also regularity of f prime. Like the first derivative need to satisfy the regularity condition. Yeah. Okay. And I will skip the proof. The proof is quite straightforward given the exchangeability. So I'll leave that to you. But we can take a look at how this alternative definition may make the calculation of Fisher information easier. As an illustration, consider one more example. So in this case, we previously looked at that a normal case where we have the mu or cosine equals a theta thing. So normal cosine theta squared in that example. So we continue from there, but now we're using the second derivative definition of phase information to do the calculation. And we can see that the resulting phase information is consistent with the one. It's the same as the one we we calculated using the original definition. So we have the same result. Just example. Another property of phase information besides these alternative definitions, additivity. So as one might expect, the information supplied by two independent observations is the sum of the information supplied by them separately. So if you have independent observations, each provides certain information about a parameter, then using the two or multiple observations together, the total phase information is just the sum of their individual phase information. Additivity. Theorem. Let x and y be independently distributed with densities f theta and g theta, the same theta, but two densities, satisfying C1 to C6. Okay, so we added C6 regarding the exchangeability of integration and differentiation, the regularity. If I1 theta, I2 theta, and I theta denote the amount of information about theta contained respectively in x, y, and jointly x and y, then I theta, the joint information, is just the sum of the two information. Okay. And because of this, then you now have NIID with the same density satisfying, again, these regularity conditions. Then the information about theta contained in the total sample equals N times J theta, where J theta is the common information contained in each individual observation. Okay, this is all expected. Okay, and this is the proof. The proof for this additivity is based on this definition. And we can actually get a square, right? We can get a square out because it's just because in this case, log joint density equals the sum of the log density. Because of the log, the joint density is the product of individual density. By taking the log, product becomes sum. That's it. And then the last one, the final expectation here can be written as expectation of this times expectation of that. And each expectation is zero because of the exchangeability of integration and differentiation. Okay. Finally, let's look at phase information about a function of theta. Again, we consider transformation of our parameter. If we're not interested in theta, but some function of it, what is the phase information after the transformation? Okay. The information I sigma squared contained in a normal observation x with no mean about theta is 1/2 theta 4. We have this result, right? Because it has nothing to do with the mean. Would the same answer obtain for the information at x contained about sigma? So essentially, we're asking about what is the phase information about sigma, not sigma squared. Because sigma squared is the variance parameter, sigma is the standard deviation. Beyond this, more generally, we can ask what is the phase information of sigma to the power k, raised to the power k. So that means we're not just interested in sigma squared, but sigma to the power k. How can we get a general formula for that? So let's do it. So essentially, we write this as eta. Eta equals to theta k, sigma k. And we first write down the log likelihood in terms of sigma in this way. And now eta is sigma to the power k. We re-express every sigma as eta to the power 1/k. Okay, then we plug this in. Okay, and we get this in terms of eta. Now we're going to take differentiation with respect to eta. Okay, we do the differentiation. This is it. And we can get phase information. Based on this, you can basically take the square of that, the expectation. And what is that? Actually, we're using the variance formula because we have the C6. We are looking at the variance of this, okay, variance of this whole thing, and the random variables x here. And this is what we get. Phase information of eta. So for k equals 2, it reduces to what we are familiar with. Just the phase information of I sigma squared is this one, as it should. For k equals 1, just I sigma, this is what we have, and so on. Quite generally, the information x contains about this function depends not just on the parameter, but also the function, the transformation. Because you can see that here we have eta equals g sigma. Okay, that's it. So essentially, g function depends on k. And as you change your g, you change your k, and this phase information changes with k. So basically, it says that the phase information is not the same thing because this one is the same thing, right? If your g does not matter, then I eta should be equal to I sigma and should not involve k. But it's not the case. K is indeed involved, meaning that phase information does depend on g, not just the parameter of interest. And is that counterintuitive? Like you transform your parameter by function g, then the feature information is transformed, it's changed. Okay, let's look at the argument detail here. The argument leading to this result can be used to evaluate this I g theta more generally. So suppose that eta equals g theta is a strictly increasing differentiable function with derivative g prime theta. Strictly increasing function, differentiable function. Expressed in terms of eta, the density f theta x then become f eta x, right? F eta x, and we are basically replacing theta by g inverse eta as this. So that when we take this density in expressing eta, take the differentiation log density with respect to eta by, again, chain rule, this is what we get. Okay. And you see, this is what we have for the original log density differentiation. And we have this additional term. And this phenomenon also happening in our change of variable in density, right? But here we're not doing change of variable, we're just doing change of parameter. And then therefore you can naturally see that by taking this squared, and expectation. Essentially, this is our phase information for eta, this is our phase information for theta, and this is what we get in the denominator. So how can we interpret this? Essentially, we're saying that based by transforming the parameter, depending on the transformation g and how fast it changes at the current theta, it will change our phase information. The larger g prime theta is, the smaller the post-transformation phase information is. The smaller g prime theta is, then the larger the phase information after transformation. Okay, let's first read this explanation to see whether it makes sense to you. Then we can go back and use my language to express it. It can be seen from this formula that a more rapid change in g theta, that is, an increase in g prime theta, will decrease the phase information of g theta. To see why this is reasonable, suppose that I theta and hence the accuracy with which theta can be estimated is fixed. Then g theta can be estimated more accurately the flatter the function g is at theta. Since a value g prime at a given small distance from theta will lead to a small deviation from g theta. So in other words, it says that if g is flat at theta, then even if your estimation of theta is not so accurate, you can still make your estimation of g theta pretty accurate since it doesn't fluctuate much. However, if the g theta changes a lot, that means it's very sensitive to your estimation of theta. Then you cannot estimate g theta very well. Does that make sense to you? Yeah. So the most extreme case of this phenomenon occurs when G prime theta is 0, which is flat, in which case you have infinite information for estimating this G theta. Because if it's flat, then you can guess it, right? Your estimate of theta accurate doesn't matter. In this case, the function G is essentially constant in a sufficiently small neighborhood of theta, so that only the rough idea of theta is needed to get very precise knowledge of G theta. A more quantitative interpretation of the phenomenon is obtained by recalling, okay, let's just forget about that. Yeah, but it's actually related to delta method. Yeah, in chapter 2. So this is a delta method. Remember, what is this? This one tends to in law to what? Delta method. Oh, actually, this is root n. Let me see. Okay, let's forget about it. I'm saying this is actually the case. Okay, let me just write the delta method and then let me get back to here. So delta method is this. G theta hat m minus G theta convergent law to okay, this is what the delta method should tell us, because I'm just taking the asymptotic normality of MLE and then I apply delta method. So the asymptotic variance will be multiplied to the square of the G prime theta. That's essentially it. But this delta method result will break down when G prime theta is 0. Because when that is the case, you have a 0 asymptotic variance. That will indicate that multiplying root n may not be enough. So you may need to go to n times this thing. And to get a limiting distribution there is typically like a chi-square distribution instead of a normal distribution. Because now you need to go to the second order in your Taylor expansion. So like the G double prime thing using that term. And that is a square term. And that term will converge to a chi-square distribution instead of Gaussian. Because the first order term is just linear, right? And that is based on central limit theorem is normal. So I'm just skipping a lot of details, but trying to say that this is application of the delta method. And you can also see this result related to this result. Because here we're saying that when G prime theta is 0, you have infinite fish information after transformation by G. And this can also be seen here. If you have G prime theta being 0, then your convergence is actually faster than root n. Root n is not enough to stabilize the distribution. And that also tell you that your estimation for G theta is better, is faster, it's better than just for theta. Does that make sense? Yeah. Oops. Okay. Okay, I think that I can skip the remaining part of this part about facial information. The take-home message is that facial information is useful, but it's useful only when the asymptotic normality of MLE holds. That is the condition of using facial information. Okay, and it provides nothing beyond the asymptotic variance in that limiting distribution. And we still need to check C1 to C5 to get the MLE's consistency, MLE's asymptotic normality. We need those 5 conditions. But if we want to use the alternative definitions of fish information, we need additional regularity, which is basically exchanging your differentiation with integration. You may need to require that for the second derivative. Okay. Okay, now let's move on to the asymptotic normality theory. Why this holds, right? We want to make it more rigorous. The present section will further develop the theory of likelihood-based estimation in 2 directions. First, we shall discuss conditions under which the asymptotic normality result holds and give a proof of the resulting theorem. This will be followed by consideration of the problem arising when the likelihood equation has multiple roots. That is, when you set the first derivative of log likelihood to 0, you may have multiple roots, multiple solutions. The guaranteed existence of a root that is consistent and hence satisfy that asymptotic normality, just say that asymptotic normality is then inadequate since it does not tell us how to find this root. We shall discuss some ways to get around this difficulty. The following theorem gives sufficient conditions for the validity of the asymptotic normality, which has been used in the previous sections. Now let's look at this. Let x1 to xm be IID with density of theta x satisfying C1 to C5. We've seen that again and again. And suppose that in addition, we need a C6 double prime. So you see, we're basically strengthening this beyond that regularity condition we require for the alternative definition of Fisher information. So this one is stronger because we are now talking about 3 times differentiable. So not the first 2 times, but 3 times. And the third derivative is continuous. So we now require that integration and differentiation hold for the third derivative, not just the first 2. Okay, so that's why it's C2 double prime. Besides this, we also need some upper bound on the third derivative of log likelihood. So if theta 0 denotes the true value of theta, there exists a positive number c theta 0 depending on true parameter value and the function m theta 0 at x such that you have this upper bound. You bound this absolute value of third derivative for all x in your domain, distribution domain. And you need this upper bound to have finite expectation. Yeah. So this is just to ensure that you don't have some radical behavior in your third derivative. That's it. Then any consistent sequence, MLE, depending on sample size n, of roots of the likelihood equation satisfies asymptotic normality and Fisher information bounded away from 0 and infinity. Let's prove it. Okay, and this the key idea, Taylor expansion. Taylor expansion is used like in delta method and also in MLE asymptotic normality. So it's like the maybe if you want to name one for asymptotics, useful technique for asymptotics, Taylor expansion. Yeah. All right, let the small ln theta denote the log likelihood, and this our is its derivatives with respect to, oh sorry, I'm not showing it, with respect to theta. The proof is based on the fact that on the one hand, MLE satisfies that the first derivative of the log likelihood is 0, right? It's called the likelihood equation. It's a root for that. On the other hand, theta hat m is known with high probability to be close to theta 0 of consistency, right? Because of consistent result, it is convergent to theta 0 in probability. Then, if it's 0 here and it's sufficiently close to theta 0, then you're basically expanding the first derivative about this one. And this is already known to be 0, by the way. And you're expanding it to be this one. It will give us an equation for this difference. And that's the thing we want, because the asymptotic normality has this difference on the left-hand side. So that's why we're trying to link this difference to the difference in terms of the first derivative of log likelihood. Okay, using Taylor expansion. And by the law of let me see, I should turn the page here. For any fixed x, expanding this log likelihood, so by fixed x, we mean that we fix our sample. Okay, and we're only considering one observation in our sample first. Actually, not one observation, n observation. Otherwise, we wouldn't write log n. But we're saying we fix that sample. Expanding this Ln prime, I'll just say that is the first derivative of the log likelihood at MLE about the Ln prime at true parameter value is this. So you now see, because we start with this first derivative, then in this term, we have the second derivative. In this term, we have the third derivative. We have this difference and square difference. And we're using that, how to say, mean value theorem, right? So for the one, that's when we don't consider the remaining terms, because here we're not using theta 0, but we're using a value between theta 0 and theta hat n, between the two endpoints. Okay, between this and this, we know the existence of some value here that will make this equation hold. Okay. But the left-hand side is 0. This is by the definition of MLE, right? MLE definition. We have root n times this is essentially, you're just do algebra. You keep this thing on the left-hand side, you keep this thing and you divide this to the denominator, and then you also multiply by root n. So essentially, it's nothing beyond algebra, okay? And you get this one, this equation. And of course, the quantities first and second derivative depend not only on theta, but also on your sample, right? Sample determines the log likelihood. Of the three quantities on the right-hand side, so this one quantity, this one quantity, this one quantity, let's look at their asymptotic behaviors. First one, in the numerator, this is what? Log likelihood derivative at true value. You know, log likelihood is a sum, right? It's a sum of the log density at each data point. That's the log likelihood. Because it's a sum, if we divide the sum by n and multiply by root n, we get a central limit theorem. And this is a central limit theorem result. And this asymptotic variance, it should be the variance of each term in the sum, right? And that is log density. And the variance of that is actually Fisher information by the alternative definition, one variance of that. Yeah, so this is by C log T. Okay. Second one, second derivative. Now your second derivative is also a sum, right? It's a sum of the second derivative of each density, each observation's density. And you are dividing that by n. You get law of large numbers. And by law of large numbers, it's convergent to the expectation of each term in the sum. And each term in the sum is second derivative of the log density. And by the alternative definition, that's Fisher information. Yeah. So this is by LLN. Okay. I'm just, or maybe I can write a little bit out. So it may be better than what I just said. So for the left-hand side, let me just write a little bit. Okay. This is actually, I can write it as 1 over n summation I from 1 to m. It's essentially, let me see. Yes, this one and log f theta xi. So this is what I'm saying, the sum, average, multiplying by 0, minus 0. This is the mean of that. And this by CLT will convert in law to normal distribution. And the variance of this xi, right? So that's why this is Fisher information. I'm trying to just derive what the central limit theorem is like. Yeah. And for this one, 1 over n, sum 1 over n is like, okay. And this by law of large numbers will converge in probability to the expectation of one term. right? And this is minus Fisher information. That's it. Does that make sense? Yeah. So that's why these two terms, so the numerator has central limit theorem like normality. This one in the denominator first term has Fisher information as this limit. And the last one has what? The last one is bounded improbability. And sorry, okay, yeah. Last term is this one. This one is less. This last term is bounded improbability because again, we'll apply this by the law of large numbers. And we know from the condition here, we know that this one is bounded, right? This is always bounded, and this expectation of the upper bound is bounded. So that's why we say this is bounded. So essentially we're having 1 over n times this is bounded, okay? And this is going down to 0, right, in probability. So that's why this third term is shrinking. So essentially we have the numerator converging law to normal distribution. This one converging probability to Fisher information. This shrinking to 0 in probability. Then together we have asymptotic normality. Does that make sense? Yeah. So essentially, you're basically putting all things together. Let me say this again. This convergent law to normal distribution, and this converge in probability to Fisher information, and this converge in probability to 0. So that's why together, this will converge in law, and you have this Fisher information in the denominator, and you will enter this in the, how to say, and this is actually entering this. So essentially, we're getting that's it. Yeah. Yeah. So that's why we get this Fisher information in the denominator. Okay, I just give you a sketch of the proof for this, and the details are all in this textbook. So I'm going to skip that. But essentially, we will tell you about lemma. Let me see, we need that. Let's look at this lemma. Application of the theorem requires checking its various conditions. Differentiation under an integral required for C6 to C6 double prime is about the exchangeability of integration differentiation. It's treated in books on calculus. Yeah, the following conditions typically are easy to apply. Let's look at some conditions. Easier than that. So a sufficient condition for h theta equals g theta x integrates x from a to b to be differentiable under the integral sign for h prime theta to exist and be given by. So essentially, the differentiation should have it outside integration, but we're now moving it inside, right? How can we make sure this hold? Yes, it's about this exchangeability condition. For given by this at the point theta equals theta 0 is that for some theta 0 between theta 1 and theta 2, the function g, here the function g, has a continuous derivative with respect to theta in the closed rectangle, x from a to b, theta from theta 1 to theta 2. So essentially, x from a to b is in the integral. It's already here. And theta, you are trying to get some lower bound, upper bound of it to get an interval of it. And you're trying to say that the g has continuous derivative for this interval. So again, it's about continuity. Continuous derivative thing. If you have that, then you can change the two things. That's it. Yeah. So it's a technical thing about the regularity. And if the range of integration is infinite, so now a to b becomes negative infinity to positive infinity, it is required in addition that you need this uniformly for theta in some neighborhood of theta 0. So actually it's about the continuity of derivative needs to be uniform, not just continuous, but uniformly continuous. Yeah, again, regularity. So that's about the technical thing. I think we can probably stop here. Yeah. And for this result, we're just trying to show example. We can probably visit this next time. The Poisson example is just trying to show that the conditions we can check and they hold. So that's why the asymptotic normality for MLE holds. Okay. All right. So the take-home message for this part is we need regularity condition for that to hold. That's pretty much it. So the likelihood is well behaving. So you can get a derivative, first derivative, second derivative, third derivative for the log likelihood. And also for most of the cases in applications, we use distributions like Poisson to model our data or Gaussian Poisson. So that's why MLE is very well behaving. Okay. All right. So I will see you next Monday. Okay. Thank you.